In this lecture, we will talk about Unit 3, Structure of Matter and Chemical Elements. We will talk about models and theories. We will also look into the states of matter, the liquid, solid, and gas, and the properties of each. We will look at elements from the periodic table. We will then we'll take into a deeper look into the elements, and we'll look at the atoms and structure of atoms. We'll talk about ions, isotopes, and the difference between both. And then at the end, we'll finish up with the structure of elements. Okay. Before we get into any of these, let's talk about scientific models. And models are generally made so we can understand certain chemical reactions and certain chemical phenomena. So a model is a simplified approximation of reality. So what you're looking here, this is the double helix structure of a DNA. Now, if you take a tissue, or if you take a slice of a tissue, and try to study the protein of that tissue, and you try to study the DNA and look at that DNA, obviously it's not going to look color-coded with oxygen, nitrogen, and carbon, but we do that so we can understand the bonding between every element, and we can understand the bond length, we can understand the bond affinity and the affinity between every single element. So models basically is made to simplify reality, makes it easier to understand. Likewise, how we're going to look at the atom, for example. We draw it in a way to help us understand how electrons, protons, neutrons interact with each other. When it comes to the kinetic, to the kinetic molecular theory, every time you see the word kinetic, what I would like you to think of is movement. Okay, so kinetic molecular theory means that every matter, doesn't matter if it is a solid, liquid, or a gas, it does consist of small, tiny particles that are in constant motion. Once you increase the temperature for these particles, once you expose that matter to source of heat, you are going to break the bonds between these particles and increase the motion of them. Okay, so that's what basically kinetic molecular theory means. It means a constant movement for these particles. Every matter has particles, and these particles are in constant movement. Temperature changes the status of movement for these particles by increasing the energy of these particles. The state of matter, I'm assuming that everybody here have heard about this before, the solid, liquid, and gas, correct? So solid, liquids, and gas, they are different in the degree of freedom of their particles when it comes to their motion and ability to move within the medium, and also how strongly these particles are bonded to each other and attracted to each other. So when it comes to the solid state, for example, it has a constant shape and also has a constant volume. So if you, for example, take the book that is sitting on your table right now, your chemistry book, that one will have the same shape and same volume. It doesn't matter how long you leave it on the table. Now, as long as you don't expose that to a source of heat, obviously, and you don't turn it into ash, then you will change the state of that matter. But generally, it preserves the same shape and volume. Now, why? Because these particles are strongly attracted and packed to each other. But despite that fact, there is still some sort of movement, and there's a vibrational movement for these particles that we can't really see with our own eyes. But even at a solid state, these particles are in a constant oscillating movement, very small and tiny vibration, while they are attracted to each other. These particles try to change direction and velocity, but obviously because these particles are very close to each other, it makes it nearly impossible to change direction and velocity. Again, each particle is trapped in a small cage. So, and these cage walls basically made from other particles, and they are very strongly attracted to each other. So that makes the movement very difficult. So these are the properties of the solid material. So the nature of the solid can actually change. We can change the solid into a liquid, and eventually it can also change to a gas. But before we get into this, if you take an example of your car engine, obviously all the particles within the material, within the steel in your car engine is really packed to each other, very small, as you see in the blue region here. So you can see particle 1, 2, 3, 4, and 5. They are very small. You can see there is almost nearly no space between them, and they continue to bump each other. Okay, so that's when the car engine temperature is kept low to the point where the particles within the steel, the bonds between them is not going to break off. But let's assume that the temperature, it is going to increase, which would result in extensive and increasing the temperature of your of the steel material, or the solid material in the car engine. What happened? That these particles, it is going to cut loose from each other. They are going to increase the space, and all of a sudden, these particles are not really packed and close to each other. So as temperature rises, the particles move faster and bump to each other, and bump harder to each other. Okay, and you can see the neighboring particles, for example, between 4 and this particle here, they are further apart from each other once the temperature started increasing. Now, once the temperature starts increasing, the volume will also increase. So, your piston volume is going to increase, and also your engine steel material volume is going to change, and that's obviously we don't want it to happen for the car. Now, the reason for that is because there's a friction. There's a friction between every element in the car engine that's causing the increase in temperature. Okay. Now the friction is coming from moving parts within the car, which is the piston going up and down. Okay, so it is important to keep the temperature in the car engine low by having lubricating material and other elements to keep the temperatures low. Otherwise, the particles in the steel and the solid material is going to break off, and then it will change and reach the state of liquid. Okay, and that's what we call it melting. So when the internal energy of the solid increases, typically by the application of heat. Okay, so by increasing the heat, are you increasing the internal energy of the solid particles, of the tiny particles, until it reaches a change in the physical state. That's what we call it a melting point. So melting is a physical process that results in the phase change or phase transition of a substance from a solid to a liquid. Once that transition is completed, we will say the material has melted. It has transformed from being a solid, particles are close to each other, to a liquid state, or particles are further apart from each other. Okay, and that's due to increase of internal energy of these particles. Once the energy is increased, internal energy, the bonds and the cage between these particles start break off, and that's where the change in matter, take place. At the melting point, the ordering of the particles in the solid breaks down to a less ordered state. What that means that there is no structure anymore. It's in fact has been replaced with more freedom and more movement. So that takes us into the liquid state. The liquid state has a constant volume but a variable shape. You will see that in the lab. For example, you're trying to measure a 25 ml or 20 ml of water. You will use a graduated cylinder, which basically looks like a tube or a cylinder. But then later you'll transfer that 25 ml into a 100 ml beaker. So all of a sudden that volume has changed its shape from being in a cylinder into being into a beaker. So the volume remains the same, but the shape has changed, taking the shape of its container. The particles are moving fast enough so they can break attraction and form new ones with other particles. So each particle in the liquid is constantly moving. From one part of the liquid to another part of the liquid. So if you look at this Oppenheimer flask, for example, you have the liquid in there, and then you have the particles are, sitting next to each other. But obviously, if you compare them to the solid, you can see how far apart each particle from each other. There is more movement, so you can see these bows here that basically indicates a movement. And you can see how these particles really have a larger degree of freedom compared to the solid that we looked at earlier. So the particles are moving fast enough so they can break attraction and form new ones. Particles are less organized, so there's more chaos, there's more freedom in movement, and slightly more space between them compared to the solid. So if you take a snapshot of this side of the Oppenheimer flask, and you assume there is a particle. If you put a tracking device on this one, you will see this particle going all the way up there. Okay, so So this particle can move from this side all the way to this side. And same thing applies to all particles of that liquid. Now, you can probably see this if you drop, like a small, like blue dye, for example, you will see it dispersing and traveling all over the liquid. That's because every particle is constantly moving and carrying that dye all across the flask. Okay, so that's what happens. That's in terms of liquid. So more degree of freedom compared to the solid. As we talked about melting earlier, evaporation is equivalent to the melting. However, with evaporation, we're changing from liquid to gas. So that's the difference between evaporation and melting. It basically has the same physical concept. However, we're changing from one state to the other. And when I say physical concept, that means it also takes place when a liquid is exposed to a temperature. So when you increase the temperature, you're increasing the internal energy for these particles, breaking off the bonds, and then eventually these particles are going out to the air as gas. Okay. If you take a pot and put it on the stove and you start heating the water in that pot, eventually you'll see small tiny bubbles, and later that bubbles will get even more vigorous, and then at some point you will see, you start generating gas or water in its gaseous formation or vapor. Okay. So evaporation is when the molecule of the liquids collide, they transfer energy to each other. So on top of the energy that you're adding, there is energy being transferred between every single particle. When a molecule near the surface absorbs enough energy, breaks that bond and goes into the atmosphere, it escapes, forming the gas. Okay? So that's evaporation. So keep in mind and try to differentiate between melting and evaporation, melting point and evaporation. So that takes us into our last state of matter, which is gas. So the gas has a variable shape and volume, right? It has a large degree of distance between the particles. For example, a gas cylinder or a gas within a gas cylinder, you can basically just open up the gas cylinder and let the gas go in the air. The gas will occupy the volume of the entire room, for instance. So the volume in that small, tiny gas container, it can go and spread all over the room. So the shape is different. So now it's no longer sitting in the cylinder. And also the volume is different. Now it has gained or now occupied larger volume. Constant collision between the particles leading to constant change in direction and velocity. And we'll look at that one in a second. So if you look at the emission of the car, or the material that comes out of the running car engine, obviously you're using liquid and then you're transferring that into a gas. The gases that comes out of the car, either nitrox gases or methane or carbon monoxide or whatnot, it is coming out in gaseous formation. So the particles are really farther away from each other. And then eventually you will see that gas basically will just go and disappear in the air because these particles are gaining even more space and they're willing to be away from each other. Okay, once these particles end up meeting each other at some point, they will bump into each other and it will also depart away. So even more space and more volume is being gained. So that's the difference between the gas, the liquid, and the solid. So the solid, let's look at it here one last time. The state of matter, the solid has a constant shape and a constant volume. With a solid, the particles are caged, trapped next to each other. There is really almost no degree of freedom. However, there's still oscillating movement for these particles. Okay, when it comes to liquid, larger degree of freedom. Particles are free to move and change location, break bonds, and form others. In the liquid, the shape is variable, but the volume is constant. It doesn't change. The gas is against everything the solid and liquid stands for. It has a variable shape, it has a variable volume, and there's definitely a larger degree of freedom for the particles in the gaseous formation. So that's when it comes to the state of matter. Now let's look at the elements. So every time we talk about elements, the first thing obviously we'll talk about that in a second too, is the periodic table, because the periodic table is like the Bible when it comes to the elements. It has all the information that we need to understand and we need to know about the elements. So chemists learn about the world around them um, by taking things apart. So you break things off in order to study really chemistry and really to understand why certain reaction take place. You need to break them apart and study every element and study the chemistry and the electrons of every element so things can be explained. So everything boils down and goes at the end to the elements. That's basically the bottom line. What are the most basic what are the most basic building blocks of our universe? Elements are the building blocks of our universe. Okay, so that's why we study our universe based on the composition of either fossils or even looking at the universe and looking at the remnants of explosions and stuff like that. You look at the elements and you understand historical scientific events. Okay. So, what does element exactly mean? Element is the simplest, fashion or the simplest form that you can explain a substance. Okay, so when I say element, there is no further simplification for the material. So it's the simplest, the substance. It's the simplest way that you can represent a material. Okay, let's put it that way. So if you take an example of salt in water, and you try to do distillation, and if you're not familiar with distillation, it is a physical process where you boil certain material, okay, and you have a where you have a cold bath, basically capture the material back, and whatever residual you have in your flask, that's basically either the impurities or other material which has a different boiling point. So it's basically separating material based on their boiling points. That's what distillation means. So if you take a salt water and you start boiling that material and doing distillation, obviously salt has a different boiling point than water. So first you will boil the water and then it will have residual of a salt sitting in the flask. So we'll have the salt and you'll have the water. So we separated both materials from this solution, and we will look at solutions also, I think in a couple lectures. But here let's focus on water and the salt. Now the question: can I break the salt down into a simple, simplest form? Yes, I can. If I run an electric current through the salt, I'll break it down to sodium metal and also chlorine gas. Likewise for the water. If I run an electric current through water, I can basically generate oxygen gas and hydrogen gas. Let's ask the question one last time. Now, can I simplify sodium? Can I simplify and make a simple extraction out of chlorine, hydrogen, or oxygen? The answer is no. This is the simplest way that you can explain. This is the simplest form that you can reach at this point. So these substances are elements because they cannot be broken down. You cannot really break it any further into a simpler substance by chemical reactions. That's what the element means. So it's the simplest substance at which you can't really break it down through any chemical reaction. That's what the element means. All right, let's talk about elements and learn some facts about the elements from the periodic table. So there are 94 occur naturally elements on Earth. 24 it's made in the lab, synthetically made. Iron is the most in abundance on Earth. Oxygen makes the most common element on Earth, obviously, because it's part of our of the atmospheric air. And only 17 elements are known for certain to be necessary for human life. Now you might think of oxygen, hydrogen, nitrogen, carbon, phosphorus, sulfur, so on and so forth. So these elements are essential for the human life. Without them, planet Earth won't be livable. Okay, so let's get now to the periodic table. And so each element is known by name and symbol. So if you look at this one, so this is an example of the periodic table. Everything here, if you look at the lithium, beryllium, boron, carbon, etc., it has the name of the element, which is lithium. It has the symbol, and it also has two different numbers, which we will look at in a second. The elements are organized in the periodic table for a reason, in a certain way. They are not just arbitrarily thrown in the periodic table without the scientific reason behind it. So the elements in the periodic table in a way to make organized in a way to make it easy to find and also to understand their chemical properties. For example, chemical in the same column in the periodic table, the vertical column in the periodic table, which we call it also group, tend to have similar characteristics. They're not the same, they are close, they exhibit similar characteristics. That's why we refer to them as a group of families. Okay, so what that means if you look at all the groups in the halogens right here as it is labeled, sorry. These are the halogens. This is the group of halogens. All these elements, they tend to have the same, or similar chemical properties and similar chemical reactivity and reaction tendencies. Okay, and we call that a group of families. The horizontal row on the periodic table is called period. So every time you go across the periodic table from left to right, we call that one period. Up and down, we call that one group. So it's important to know these terms. So we have 7 groups and we have 8 groups in the periodic table, and we have 7 periods. The number that you see here on the top, this is number 1, 2, 3, 4, 5, 6, 7, and 8 group. Now the groups in the periodic in the center of the periodic table, which is the transition metals, these things I'm not going to worry about for now. Okay. So these are the groups in the periodic table, and then you have the period numbers on the side. The group names, I would like you all to memorize and know and understand the group names for these, because we will be referring to them now, starting from now, and even moving forward when we're talking about chemical bonding. So I think for you, in order to understand why ionic bond and covalent bond would form, it is important for you to understand that sodium, for example, belongs to the alkali metals, to group 1, or the alkaline alkaline earth metals, like the magnesium in a group 2, the halogens, fluorine and chlorine. So these nomenclatures, and the noble gases as well, these nomenclatures, I expect all of you to be familiar with. Okay, so these are the names for the groups in the periodic table. So when I say potassium, for example, I would like you to immediately know that potassium belongs to group 1 and also belongs to the alkali metal group. Okay, because all these groups, the alkali metal, they will have the same oxidation number, for example. The halogens, likewise, they will have the same oxidation number, and they will have a very similar chemical properties. So it helps you to know the names and how we label all these, every group of these. Okay. Beside the name of the groups, the periodic table has 3 different characteristics when it comes to properties of elements. Okay, we have the metals, the nonmetals, and also the metalloids. So everything to the right corner of the periodic table, we call these the nonmetals, and they belong to the big family of the nonmetals, and we will talk about their properties in a second. The staircase that you see here, we call this the metalloid. So those folks, they exhibit the properties of nonmetals and metals at the same time. So it's a combination of both. The metals is everything else that you see in the periodic table. So if you look at this one here, so you see everything here in the green, this is considered non-metal. This one here, these are the noble gases. Everything else is considered as metals. Okay, you can see it on this one. These are the metals. These are the metalloids. Okay, and these are the non-metals. Now, why is it important to know which one is a metal, which one is a non-metal? Because based on being as such, it really helps to know when the covalent or the ionic bond is going to form and why it is forming. We'll talk about bonding, of course, in I think a couple lectures. Classification, we have the main group, which is the 2 blocks in the periodic table, the transition metals in the center, and we have the lanthanides, or the inner transition metals, in the bottom. The part that I would like you, or we are going to focus on for our course, is going to be the main group elements. Transitions and lanthanides, those are different chemistry that we're not going to focus on during this course. So you might be confused because we talked about 3 different or 4 different things about the periodic table. And your question would be like, okay, so which of these nomenclatures should I worry about? Metals and non-metals definitely should be on the top, and then the names of these two groups as well. So I want you all to know that argon is part of the noble gas, helium is part of the noble gas. And same thing when it comes to metals and non-metals. Okay, so let's talk about characteristics of metals. Metals have a shiny metallic luster. Example: gold. Gold is a metal, right? I mean, silver. All these, silver and gold is metal, and they are obviously shiny. That's why they use them for jewelries. Metals also conduct heat as well as electricity. They both conduct heat and electricity. Now they have different resistance for both, but they both some of them are more efficient than others to conduct electricity as well as heat, but they both do conduct, they all conduct electricity, electric current. Okay? Metals are malleable. Example, gold, right? Because we make jewelry out of it, so you can turn it into a thin sheet without really breaking it into parts, right? Because of the type of bonding within these atoms in the gold. So it is malleable. It conducts electric current, and they are also shiny, shiny luster. Now the exception for this one is mercury. Mercury is a metal, however, it is in a state. It is in a liquid state. Okay, so that's the only exception in the periodic table. Characteristics of nonmetals. It's basically the opposite of the metals. So nonmetals mostly lack characteristics of metals. So anything the metals exhibit, the nonmetals will have or will be against. Okay. So it tend to have a relatively low melting point, boiling point, and also density. So, for example, if you look at the periodic table, gas, like the oxygen gas and the nitrogen, they're both non-metals, okay? And they both have a low melting point, right? Because they're already in the gas state, and also the density is low for these. Typically brittle when solid, and if you try to expose them to a stress, you'll basically break them into pieces. And they are usually poor when it comes to conductivity. I'm not sure when was the last time you heard about carbon fiber, for example, is used to conduct electricity or to use cables out of them. Never, correct? We use copper or we use aluminum, for electricity and for heat. Copper used most of the times for electricity because of the high efficiency and low resistance. The nonmetals also tend to have relatively high electron affinity, or we also call it, excuse me, or we also call it electronegativity. So this one, what electronegativity means is the passion or the tendency or the ability for an electron of atoms to draw and attract electrons. Okay, so nonmetals, they tend to have a high electron affinity or high electronegativity. Now, what does that mean? This actually means a lot when it comes to bonding and chemical bonding. So I would like you to highlight that thought in mind when it comes to electronegativity, because we are going to go over this when we talk about chemical bonding. Specifically, it means also the gain or share of electron. They gain or share electrons when they react with other elements. What it means also in the same time, they never lose electrons. Like oxygen, carbon, fluorine, they always gain electrons. They never lose electrons. So that's why they tend to have either ionic bonding with the electrons that always lose electrons, like group 1 or group 2, or form covalent bonding if they are forming diatomic molecules. Okay? Hang on to that one. We'll go over it more in details when we talk about chemical bonding. But it's important to keep in mind that non-metals always gain they never lose electron. Okay, so frame that up and keep it on your notes. What makes one element different from another element? It's basically its electron configuration, the protons, neutrons. So now we're talking about the subatomic configuration when it comes to the elements. So the answer that we need to look deep into the atom. Atom is obviously the smallest part of the element that retains the chemical characteristic of the element itself. Just like how when you look at any cell in the human body, right, The DNA determines the function and how every cell in the body is going to operate. The electrons, the protons, and neutron, they basically have the same. They have the same objective. Okay, so they operate the same way. The protons, neutrons, and electron inside the atom will determine how this atom is going to look like, and if it is going to be a metal or non-metal, gain electron or lose electrons. Okay, so now we need to focus on the atom. So example of a chemical characteristics, how it combines with other elements to form a complex substance. Okay. So when it comes to the atom, it's obviously very small and tiny. It has a 10 to the power negative 10 diameter in meter. Okay, so you can imagine how small it is. How small it is. If the atom in your body were in 1 inch in diameter, you would bump your head basically to the moon. Huge number of atoms in even a very small sample of the elements. So like a half a carat diamond has 5 times 10 to the power 21 of atoms. If you were to put them next to each other and line all these atoms next to each other, it would stretch all the way to the sun. So you can imagine how small and tiny that atom is and how they are close are to each other. What is the atoms composed of? Neutrons. And the mass for the neutrons is 1.00867 Dalton. And their position, or their sitting in the nucleus inside the atom. The protons, it has a positive. They are the positively charged particles in the atom, and it has a mass of 1.00728. So you can see how the protons and neutrons, they're sort of close to each other. And the electrons are the negatively charged particles, obviously, and they are very small and tiny compared to the protons and neutrons, and they are outside the nucleus. So the mass for the electrons is 0.000549 Dalton, and in case if you're curious, every 1 Dalton equals 1.66 times 10 to the power negative 24 gram. Okay, so it's a very small amount. It's a very almost hard to detect. Now that's why when we are looking into mass of the atom, we always focus on the mass of the nucleus. The reason for that is because the electrons carry on a very small and tiny mass, so they are sort of very negligible when it comes to the total mass of the atom. Additionally, the electrons, beside their small mass, they are small in size as well. Okay, and we will get into the electrons in a second. But let's talk about the nucleus first. So the nucleus, it is in the core of an atom, right, where you see all this high density of material in the center. Consists of protons and neutrons. Almost all of the mass of the atom and its positive charge are found in the nucleus, in the center of the atom, right? We talked about this because electrons are very small and tiny in mass compared to the protons and neutrons. Okay, so the positive charge of the nucleus is right in the center. Protons, the number of protons in the nucleus of an atom is called the atomic number. So if you look at the periodic table, this is right here. This is the atomic number. So if I look at the oxygen, this is the atomic number right here. So the atomic number, or the number of protons for the oxygen, is 8. Okay? That's what it means from the periodic table. So the first number then now we learned from the periodic table is the atomic number, which is also the number of protons. The number of protons, and therefore its atomic number, cannot be changed without changing the element. What does that mean? That when you change the number of protons, if you look at the carbon-6, if you add another proton, now it is 7, we change the identity of the element. So now it's no longer carbon, it is nitrogen. What that means again, that when we are doing chemical reactions, when we're doing chemical bonding, we don't gain nor lose protons. That's very fundamental for you to keep in mind. What we gain or lose is electrons, because when we change the proton, we change the identity of our element. and that it's not, this is just not possible to happen in any chemical reaction. So this is another thought that you need to keep in mind. So the number of protons, again, which is its atomic number, you cannot change it without changing the identity of your element. Neutrons, however, is the sum of the numbers of protons and neutrons in the nucleus of an atom is called the mass number. So the neighboring particles next to the proton inside the nucleus is neutrons. So if I were to draw the nucleus like this, I will have protons, positive charge, and I will have neutron, which are the neutrally charged particles, and you have the electrons surrounding the nucleus. Okay? So the number inside the nucleus of the neutrons and proton, it's called the mass number. Let's go back to the periodic table. All right, let's go to our buddy, the nitrogen. So we have the atomic number, right here. And now we're looking at this number down here. This is called the mass number. Okay, the mass number and the atomic number are not the same. The mass number is the number of protons and neutrons combined together. Okay, this one is the number of protons only. Now, what can I get from this information? If I subtract 7 out of 14, I'll get 7. I'll get 7, correct? So that's the number of my neutrons. So if I were to give you the periodic table and ask you to look at the oxygen, correct? And ask to tell me what is the amount of protons. First thing you will look at the atomic number. So then I'll have 8 protons. And then I'll ask, well, what is the mass number? The mass number will be 15.9 or 16. What is the number of neutrons? The number of neutrons will be 16 minus 8, which will be 8 neutrons. Okay? Please keep that in mind. Now, why the number or the mass number isn't a fraction for all the elements in the periodic table? Because the number you see at the bottom here, like for the carbon, 12.011, this is the average atomic mass for all the isotopic forms of that element. Because carbon has different isotopes, as carbon 11, 12, 13. So they take the average mass, all these isotopes, and report that on the periodic table. That's why it's in a fraction. So if you ever do or count your number of neutrons and you ended up with a fraction, just round that number up, and that would be your number of neutrons. Okay, so if I do 10.81 for boron, minus 5, my number of protons, because I'm trying to calculate the number of neutrons, you will end up with 5.8. Round that up to a 6, and that would be 6 neutrons. Okay? So this is the information, this is the kind of information that we can get from the periodic table. Number of protons, number of neutrons, atomic mass, and also the atomic number. Okay? Let's get into electrons. Electrons are those rebel folks that they stay outside the nucleus. Okay, they don't like to be caged, they don't like to be sitting inside. They always travel, and they exist and move around the nucleus. They generate a cloud of negative charge that surround the nucleus. Now, why do we refer to the electrons as a dusty cloud? That's because electrons, they travel in incredible speed. It's almost impossible to take a picture of an electron. It requires a really advanced technology to take a picture of an electron. Because of the speed and the size of the electron at the same time. That's why we refer to it as a dust or just a cloud that surrounds the nucleus. Now, the closer that you get to the center of the atom, which is right here, the more dense the cloud would be. And that should make sense, right? Because the protons are the positive particles, electrons are the negative particles. So the positive attracts the negative, right? So the closer you are to the center of the nucleus, the center of the atom, the more concentrated the electron density will be, because the protons are dragging and attracting the electrons to be closer. The farther away that you get from the nucleus, the less electrons, or the chance of finding electrons on the outside will be less and less. So when the number of electrons equals the number of protons, what does that mean? That means when your positive particles, the protons, equal the count of electrons, the negatively charged particles, We call this one as uncharged atom. Okay, so the atom will have no charge, zero charge, because the positive is canceling out the negative. Sorry about this. Okay. Let's take an example for carbon. Let's look at the carbon from the periodic table.